we're going to get started. We're going to squeeze a lot into the next hour and a half, so I want to make sure that we have time for all of our speakers and then a panel. So if you all could find your seats, that would be great. Great. Well, thank you so much for coming to this session. We're really excited to see so many people in the audience. And today we're going to talk about the impact of quantum computing on machine learning and artificial intelligence. So, of course, the focus of the summit this year is on the edge of AI. And I would definitely consider quantum computing on the edge. And thus, it's definitely on the edge of AI, right? So we're going to talk about this cutting-edge topic of quantum computation. We have three phenomenal speakers with us today. They're each going to speak for about 20 minutes, and then we will go into a panel discussion afterwards. So please try to hold your questions for the end, and those can be asked during the panel at the very end of the session. If you have a very urgent question, we'll take roughly one question per talk during the session. Our three speakers today, first we'll hear from Matthias Treuer. Matthias Treuer has been a professor at ETH Zurich, but actually recently in January joined the Quark team here in Redmond as a full-time employee. So we welcome Matthias to Microsoft. He's the winner of the Raman Prize for Computational Physics. He's a trustee of the Aspen Center for Physics, and his recent work has really focused, of course, on quantum computing, the simulation of quantum devices. He's interested in HPC. He also has some very interesting projects on ecology and looking at marine and island life and simulating that. So he's really a computational scientist now more than a computational physicist. So we'll hear from Matthias, and then we'll hear from Nathan Wiebe, who's a member of the Quark team here in Redmond. Nathan is really a pioneer in quantum machine learning. He wrote the first papers on deep learning algorithms, how to actually execute and train deep learning models in Boltzmann machines on a quantum computer and achieve speedups. And he's also worked on qubit characterization and calibration and other areas of quantum algorithms, in particular in the simulation of physical systems for applications in quantum chemistry and material science, for example. And then we'll hear from Helmut Kotzgruber, who's a professor in physics and astronomy at Texas A&M. He's really a computational physicist, and Helmut also received the NSF Career Award. And we'll hear from Helmut around some quantum-inspired optimization algorithms that one could actually run now in advance of having quantum hardware. So let's start by welcoming Matthias for our first talk.
Thank you, Krista. We need to switch this. Yeah, so I want to talk about the quantum edge of AI. And when you look at computing, let's see, you have to, yeah, which, is this on? Yeah. Turn it on the side, it's off. Yeah. When you look at the computing, the challenge has been over millennia to get computers to work, and we still haven't solved it, so I really need AI in my laser pointer for next time. But the computing started out with the ancient Greek building analog mechanical devices to predict the process, the decisions of the planets and the moon, going to classical mechanical digital ones, electronic ones, the supercomputers, and now the next step, the edge of computing, is quantum computing. That's why Microsoft invests in a project that sounds like science fiction, but is something that we can actually build, something that can really change computing. And we don't just work on the qubits, the hardware, but we work on the full stack. We work on the fabrication of devices, the classical control, the runtime operating system, the quantum compilers for it, the libraries on top of it, the algorithms, and also the applications in chemistry and what's the focus here is the machine learning. So it's a big project, and what's exciting here is that one can really work on the full stack, which is quite rare in science nowadays. Let me start just with a simple example of what could be a qubit and how one can use a qubit. And here I want to do something already that's beyond what is possible classically, namely how do you make a random bit. Classical computing is deterministic. So theoretically in classical physics it's impossible to get randomness. In quantum physics, it's very easy. What you take is you take light, you shine the light onto a semi-transparent mirror. So half the light goes through it and half the light is reflected. And then they both hit some detector. But now, let us not send a light beam, but let us send very little light. And then light is quantized into particles called the photons. So I take a single photon, and the single photon here hits the semi-transparent mirror. And what should it do? Should it go through or not? What you do then is you ask Yogi Berra, who said when you come to a fork in the road, you have to take it. So what the photon does is it actually follows both paths, and it goes in the so-called superposition of both values. So those quantum particles can be in two states simultaneously. And then, in the end, they hit the photodetectors up there. And now I want to measure and find out where is the photon. And of course, when you look where something is, where this bottle is, then it's only in one place like here. It's not in a superposition. We've never seen that. And so when you look at it, then actually it chooses one position randomly. In this case, the 0. And that's how we get a random bit. And this is a kind of the minimal model of what a quantum computer can do, and it's already beyond what a classical one can do. So the basic idea is, instead of a classical bit that is either 0 or 1, like a light switch that is either off or on, a quantum bit can be in a superposition. It can be some amplitude times the state 0 plus some amplitude times the state 1. So it can simultaneously be 0 and 1. So while a classical bit is just 0, 1, the quantum bit can be viewed as a state on a sphere. Up, the north pole is 0, down, the south pole is 1. Or it could point to the right, that would be the 0 plus 1. Or it could point left, that would be 0 minus 1. Or it could point forward, that would be 0 plus I1. And so it can be in any arbitrary superposition. And then we look at that, and Schrödinger already did that long ago, and said, hey, it's really weird. We've never seen that in nature. And so he formulated the Schrödinger's cat paradox. So let's take a quantum state that's here, that's an atom that over time decays. And so after a while, when you describe it quantum mechanically, it's in a superposition of 0 and 1. It's partially decayed and partially not decayed. So it's in the superposition of 0 and 1, our quantum bit. And now we build a hellish device where when the bit is 1, it triggers a hammer. The hammer falls down, cracks open a vial with acid. The acid escapes, the cat dies. But now we describe it quantum mechanically. So our qubit is in a superposition of 0 and 1. That means then the hammer is in a superposition of being simultaneously up and down. So the flask is in a superposition of being closed and broken. And thus the cat is in a superposition of being dead and alive. Have you ever seen such a Schrödinger cat that at the same time is in a superposition of being dead and alive, jumping around and sleeping? No. And that is just because, like in the random number case, when I look at the cat, it's either dead or alive, and at that time it randomly chooses to be dead or alive. So the challenge in building a quantum computer is actually making a Schrödinger cat, a macroscopic device that remains in this superposition. But you cannot look at it. When you look at it, then it's either dead or alive. So the approach we take is we want to build a topological quantum computer. What we do for that is we take a state here, and that state is my qubit. And it can either be 0 or 1. So the simplest way is to simply take one site here, one location that can have 0 electrons or 1 electron. But of course, I can just look at it and then know whether there's an electron sitting there or not. So what we now do is there's theory based on work also by field specialist Michael Friedman, who's a technical fellow here at Microsoft. And the idea is one takes this electron, and that's where the science fiction part comes in, and we split it into two so-called Majorana particles. So we split apart this state into two new quasi-particle excitations. And they are located in such a device. And now the magic is that looking at one of these particles, you don't know what the state is, but only together with the other one can you know whether it's 0 or 1. So by splitting the information into a non-local state, you can hide it and protect it. So you can look at this here, and I do not destroy my Schrödinger cat. So what can we do when we have that? With a single qubit, I have two states, 0 and 1. With two qubits, I have four states, 0, 0, 0, 1, 1, 0, or 1, 1. So when I have n qubits, the total of 2 to the n possible states is all possible bit patterns of n bits. To simulate 10 qubits, I need 16 kilobytes of memory because I have to store 1,000 complex numbers. That I can calculate on my smartwatch. For 20 qubits, I need 16 megabytes. That will take milliseconds on my smartphone. For 30 qubits, I need 16 gigabytes. That needs a laptop. 40 qubits, I need 16 terabytes. That needs a pretty large cluster. When I go to 50 qubits, then I would need a machine with 16 petabytes of memory. We may have that soon. We don't have it yet. The world record is by Stammen and Thomas. They are here in the audience. Why don't you stand up? They have the world record for simulating qubits. They ran a 45 qubit simulation using half a petabyte of your memory on one of the largest supercomputers in the world. So that's kind of what we can still simulate. Then when you go to 250 qubits, then you've really reached the edge. Because for 250 qubits, you need more memory than there are atoms in the visible universe. So when you get to that size, then you have a machine that you cannot simulate anymore. Now the question becomes, when you have such an amazingly machine that's at the edge of the universe in terms of computing capability, what do we do with it? And Feynman proposed already that you can use that to enormously accelerate many calculations, because these qubits can be in these superpositions of all possible states, 0, 1, 2, 3, 4, 5, and so on, all possible inputs. And you can run a program simultaneously on all these possible inputs. Applications we see, okay, first of all, you could say beyond about 50 or 60 qubit, it gets hard to simulate it. So you can do some random program that you run and that you can no longer simulate. That's nice. But what we rather want, we want to find the first applications beyond that. And we found applications in chemistry. We found ways to analyze how nature breaks up the nitrogen molecule into ammonia, which may lead the way towards what's making it cheaper to fertilize in the future. We may use it with about 100 qubits or 200 good qubits. We may use it to design a new catalyst for carbon capture. The material science, we may use it for new materials, the superconductors, dyes and more. But for this purpose here now, when we have a few more qubits, then I think we can do great things in the machine learning. And that brings me now to the link between machine learning and quantum computing that we'll focus on in this session. And the first application is an AI edge for quantum science. My postdoc last year approached me and said, let me use machine learning for describing quantum states. Let me simulate a quantum model using techniques from the machine learning. And told him, oh yeah, sure, do it, go ahead. But don't be too optimistic, because people have spent decades inventing good description of quantum system. They spent years and they have theorems showing what is the best representation of a quantum system. But it's worth doing because it's interesting and exciting, and AI is really a hot topic. So then he did, and I was quite surprised when he then came and showed me that a simple restricted Boltzmann machine with just a few more hidden nodes than visible ones can learn non-trivial quantum states, can predict the time dynamics of quantum systems better than the best known classical methods we have that uses about the same memory. So it seems like in many other fields of machine learning that just doing it brute force with the network is better than what people have done manually before. So in that now has caused quite the change. And many people try out new types of networks to see how machine learning can help quantum science. The next way it helps is that when you want to build this quantum computer, then there are lots and lots of gates here, and they have to find the right voltages everywhere to make it work, to really make this electron split into two Majorana particles. And for that, when you just look at it and switch on the qubit, then it looks bad. You get scans like this or that. And what you want is the function of the voltages is some graph come out that looks like this or that, a really nice and clean structure. And in these structures, one can then sit on these edges, and that's where the qubit operates. But first you have to find it with many controls, and that's where the quark team works on using machine learning to tune up those qubits. For one qubit, you may still do it manually. Once you go to 10,000, it should be automated, and that's where AI gives an edge to quantum computing. Once we then have the quantum computer, then we go now to the quantum edge of AI. Then we can use quantum computing to help AI. One way is we can do quantum training. We can train a classical network using a quantum machine. For example, any like a sampling method can be accelerated quadratically by quantum machines. Or you can train even a quantum model. Instead of a classical network, let's build a quantum network. And because a quantum machine of a size of 250 qubits can no longer be simulated by the universe, this is more powerful than any classical machine, and it may be very useful for AI. More on that will be the talk by Nathan Wiebe, who speaks after me in the session. But that will still need a quantum computer. And it's still a few years off until we have that machine. But until then, already in the last years, we looked at quantum optimizers, like the machines from D-Wave in Vancouver. They built an optimizer that works based on quantum principles. And looking at that, one sees that it allows to escape a minimum by quantum tunneling magically through a barrier instead of climbing over it. And so looking at the mechanisms, how such a quantum optimizer works, one can then realize that, hey, I can mimic that classically. I can find ways of making use of similar effects classically. And that way we can find classical algorithms that are often orders of magnitudes faster than known ones, so that on a simple PC, you can run problems that would have needed the quantum machine or a big supercomputer before. That will be in the last talk by Helmut Katzgraber in this session. So I wanted to show you that with quantum machines, with the qubits, we can build machines that are more powerful than any classical machine can be. Starting from AI, we can use AI to help us build a quantum computer. Then we can use this quantum computer to get to better machine learning and build a quantum AI. But in the meantime, before we have that, we can already use what we learn about quantum computers to build this quantum-inspired AI, which are classical methods that work on classical computers, but where we have the ideas because we thought a lot about quantum. And so these are the two areas of the next two talks. Thank you. Nathan? This is the pointer.
It's the hookup.
But that's Helmut's. With your
Right here, I wasn't given one.
you can use this one.
Great, thank you. Great. Well, thank you very much, everybody, for coming. Today, I'm really excited to get the chance to talk to you about something that I really feel is kind of at the forefront of machine learning and artificial intelligence. And in particular, what I'm going to be talking about is the promise of quantum neural networks. So, machine learning, as I'm sure you're no doubt aware, has really changed the world in ways that very few other emerging technologies have. Within a few short years, we've gone from problems like designing a self-driving car, which once upon a time, actually not so long ago, that really would have required a major research team specifically looking at just the problem of driving a particular car under a particular circumstance. Now we have basically a large set of vehicles, including this one, which one day I hope to own, which actually use these solutions in a commercial fashion. And so this really has profoundly changed the world. And this is powered by neural networks as well as deep learning. And so neural networks I find them really kind of amazing. And every time I look at this, I really think, wow, I wish I could be that creative. And maybe actually that's something that people were thinking about when they were coming up with the first neural networks, which really try to model, of course, complex data in ways that are very analogous to how the brain ends up generating correlations between things. And this actually ends up leading to very interesting behavior, where these results over here came by taking an image, which I think was Van Gogh's Starry Night, and passing it through a neural network that seems like it's got a disturbing propensity towards aquatic animals as well as, marine mammals. But anyway, sorry for that point. But the point is that these technologies are here, and they have really profoundly changed the world. I mean, one of the ways that I feel is really shows the kind of strides that we've made in recent years is also the AlphaGo AI program, which took a problem like Go, which for years and years and years was the domain of humans. No one had found an AI at all that could even remotely compete with even a decent human player until this reinforcement learning-based approach came around, which allowed them to make a, well, if you excuse the joke, a quantum leap in the technology. Yes, I'm glad I didn't hear any laughs there. So the point is that we've really seen some profound steps forward with the power of the models that we have for data and our ability to automatically process this. But then the question, at the same time though, as this has been undergoing, there's actually been a major change when it comes to quantum technologies. So as Matthias mentioned during his talk, we've realized that if we build devices or computers that utilize the very laws of physics in order to be able to extract useful computations, then we can actually do some things we never even thought possible. And so it begs the question, how do these two things intersect? Where do they meet up? And what can quantum computing bring to machine learning? And this is still an ongoing question. There's a number of basic answers to this thing. And I think the simplest thing that I can summarize for this is that if we can build a fast, accurate, and scalable quantum computer, then it can profoundly revolutionize machine learning, in part by giving us better ways of sampling, giving us new models of data, and on top of that, actually giving us new ways of enhancing privacy for data that we're already storing and processing on machines. So, but the way that we've actually looked at this most in the literature is from the question of speed-ups. What machine learning tasks can we run faster on a quantum computer? And there's an ever-growing laundry list of things that we know how to speed up, from classification using support vector machines, principal component analysis, approximate Bayesian inference. You see the list going on and on and on. Now, there's one thing that you'll note is conspicuously absent from this laundry list that I did at the top. The humble feed-forward neural network. Interestingly, neural networks are actually very, very difficult in many cases to find good analogs for on a quantum computer. The reason for this is because at some level, quantum mechanics is a linear theory. All the transformations on vectors that we end up getting from quantum mechanics as our fundamental operations are linear. And that makes it actually very difficult to represent the nonlinear activation functions that we would want in a feed-forward neural network. And this has actually stymied people for a while, coming up with nice, natural representations for these networks. And so this has led us to focus, and this is what I'm going to be focusing on this talk, on Boltzmann machines, which are they're a class of recurrent neural networks, and I feel they're the most natural way to think about what a quantum neural network could be, and more importantly, what it can bring the world. So, Boltzmann machines solve very important tasks, like classifying what this image is over here, which I'm told is a cat by the name of Little Bub. All right, I believe it might be pronounced Lil Bub, but anyways. The point is that how the neural network ends up working is you take the image data and you copy that image data down into these visible units down at the bottom. And these which are known as neurons. These intermediate ones over here are hidden units or hidden neurons, and we don't care about the values that these take. All that we ultimately care about is the distribution that's input and the class that's output over here for a classification problem. And so what we want is for it to say that, yes, this is a cat, or no, it's not a cat, just based on these neurons down at the bottom. And we have various weights that govern the interactions between these, and the task is to tune the interactions between these neurons in order to maximize the probability of being right when this device tells you whether it's a cat or not. And so the way that we do this is by tuning the energy for it. And so this is a very physics-based approach, and it makes sense in some ways that a physics-based model like the Boltzmann machine, where you're setting the energy, should be the most natural way to represent a neural network on a quantum computer. And so the way that we would do this is we would, if we wanted to train using a bunch of training images, we would take the image and a label, which is corresponding to cat or not cat, And we want to be able to assign energies to this. And then the Boltzmann machine, when you allow it to thermalize, will give us a probability distribution over these different images depending on the energies. So the ones with high energy will be strongly favored against, and the ones with very low energy will be favored. So if we have something that's a correct classification, like this is a cat and this is not a cat, those should correspond to low energy configurations. The ones that are dreadfully wrong, like this cat being not a cat or this pseudo cat being a cat, should definitely not be favored. And so that's the idea behind it. We tune the interactions between the neurons, or as we represented on a quantum computer, the qubits, in order to be able to actually mold this energy landscape. So the favorable things are low energy and the unfavorable things are high energy. That's the entire intuition behind it. Okay? So mathematically speaking, the way that we end up representing this is we basically, apart from biases for the individual neurons, is we set the energy of a configuration to just be the product of the values of these neurons. So if we take these neurons just to be 0 or 1, then we multiply all of the values of, that the neurons end up taking that are connected to each other together, and we multiply those values by a weight matrix. These are free parameters that you pick. And what you want to do is you want to use gradient descent in order to be able to optimize this, in order to maximize the likelihood of you reproducing your training data out of this. So the other connection that I feel is really evocative that this ends up giving is that you can view this energy as just an energy operator. But you can also recast that in a different language. You can represent this energy function at the top as actually a quantum mechanical energy operator known as a Hamiltonian. And this is just a diagonal matrix that stores all the energies that will be given to every configuration up there. But it has a very nice form. It's written in terms of basic quantum operations. So we can just get something like this and directly compile it to run on a quantum computer, because these are basically fundamental quantum operations that we're seeing here. And that's one of the other things that makes this really nice for running on a quantum computer. But the question is, how do we go beyond this? How do we quantize this kind of very classical model of it? And why would we want to? Well, one of the reasons is that we really would like to get richer models. We know that quantum mechanics can't be simulated by ordinary computers. So why aren't we trying to leverage this in our quantum devices to build new models for data that would be impossible currently, and also enable new machine learning tasks that arguably don't even make much sense alone in a quantum framework? And I'm going to be spending a lot of time talking about specifically that, new things that ordinary neural networks just can't do, but these things can. And so to give you an idea about how we could quantize this, is we need to take a look at the basic building blocks of neural network training. The objects that we first have, so we've got a data set. This data set tells us what tells us what we should be trying to reproduce for this neural network. It tells us, the labels that are assigned to different classes, and what we want to do is we want to try to replicate those labels as well as possible. And so what we do is we say, okay, the classical thing you have is just that data set or distribution over it. Quantumly, we imagine that being represented as a quantum distribution over a set of vectors. Classically, for a Boltzmann machine, we have an energy function that describes this landscape that gives us effectively the probability of the Boltzmann machine outputting some image. That energy function now turns to a quantum mechanical energy operator, again known as a Hamiltonian. And to make it very different from what we have in the other case, these ones, the quantum mechanical objects, don't need to be diagonal. They can be non-diagonal, and that's important, as we'll see in a sec. And the final thing is that we've got to consider some sort of an object that we want to train, an objective function for the training that we want to maximize. And classically, at least for generative training, what we want to do is we want to minimize the KL divergence, which is a statistical difference between the input distribution over the training data and the output distribution given by the Boltzmann machine. For quantum machine learning, there's actually been a lot of debate about what the right thing to do is. And our work realized that actually the best analog to use between this is this quantity known as a quantum relative entropy, which reduces to the KL divergence in the right limit. So this is actually the natural way to think, I feel, about how to generalize a Boltzmann machine in a fully quantum setting. And so basically, it ends up looking exactly the same way on the ground. What we do is we build this network of interactions between these individual qubits, each interaction is given by a particular weight and described not by just an energy number, but by an energy matrix. And what we want to do is we want to tune all of these W sub j's in order to do it. And the idea then is once you expose this quantum neural network to the training states, we want to just let it thermalize. And then in this thermalization process, make approximate copies of the input states. So the idea basically is that you feed quantum information forward onto this quantum neural network, and it learns directly from that quantum information, and furthermore, can even generate quantum states back out. Classical neural networks cannot generate quantum states. And so that's one of the things that I think is really neat about this. So the other thing is classically, with Boltzmann machine training, all we have to do to set up to decide between these classes of images is set the energy. We only have this energy landscape to deal with. If we look at this from the perspective of a quantum energy operator, that's the same as tuning the eigenvalues of that energy operator. But in a quantum land, because this thing is non-diagonal, we can also change the eigenvectors of this. And that gives us selectivity. We can aim these models a lot better in order to suppress or enhance particular patterns that we see in this. And that makes this model much richer, even if we're not interested in replicating quantum states or learning from quantum states directly. Okay? And so because I felt the need to throw some math in, one of the questions you might ask is, quantum states are complex, right? How do I figure out how to tune all of these free parameters in order to be able to actually get it to maximize this likelihood? It turns out that actually you can derive an expression for the derivative of the relative entropy. The relative entropy itself is actually extremely hard to compute, but you can actually find its derivatives pretty straightforwardly. So but simply because of the fact that this quantum relative entropy ends up depending on the logarithm of this quantum state that ends up coming out, which is an exponential in this case. So because the logarithm and the exponential kind of nicely cancel each other out, using the properties of trace and Duhamel's formula, you can go through the calculus, and then you end up finding the derivative of the relative entropy is just a really familiar form. It's the difference between the expectation values over the training data and over the Boltzmann machine for the individual terms that you have in your model. It looks exactly like the gradient does for the classical case. And that's something that's really amazing. You can take everything that you had in the classical case, not really pay attention too much about the quantum mechanical details, and the exact same formula will tell you how to optimally tune the quantum analog of your Boltzmann machines. In case you're wondering, if you want to be able to estimate the gradient within error epsilon, and you've got m parameters, the number of samples that you end up needing to number of Boltzmann state preparations and the number of times you need to read your training data ends up scaling like this. And at least in terms of the scaling with epsilon, this is optimal. So that's what we end up getting out of this. And if we take a look at doing this on a classical computer, we just can't do it. The reason why is because of the fact that this training process, unless I make restrictions on the Hamiltonian, is actually known as a BQP complete. So what we can do is we can, actually it's BQP hard technically, but anyways, the point is that we can simulate any quantum computation using this method by cooling a state down to a sufficiently low temperature. And so if we could simulate this process classically, then quantum computers would be no more powerful than classical computers, which we strongly believe is not true, based on decades of experience. So, and also separations in terms of query complexity. So that is what we end up having. So let's take a look at what happens when we actually try this experimentally. Now, until we have large scalable quantum computers, we're not going to be able to try this on big data sets like MNIST. At present, all we can really do is validate these ideas on small systems that can be simulated using ordinary computers. So here's an example of what happens when I feed in a 2-qubit quantum state into one of these Boltzmann machines simulated on a quantum computer. You'll notice that these quantum states over here look very different at the beginning. I chose them randomly from the target states that we're trying to learn using the quantum Boltzmann machine. But only after 5 epochs in the gradient descent algorithm, you actually can't tell the difference between them graphically. So these models are learning these quantum states incredibly quickly. And furthermore, when you just let them run, they generate these states. So another thing that you might ask is, well, how much richer are these models? What do they give? Well, again, until we have bigger systems, we can't know the full answer to this question. But in small examples, we've compared what happens when we train a classical Boltzmann machine to the quantum Boltzmann machine with a differing number of hidden units. One of the things that's actually kind of interesting about it is we found that in this case, what happened is as we started increasing the number of hidden units, we really actually didn't see a systematic improvement in the accuracy of these models over here. Classical Boltzmann machine, we did see an impact of increasing the number of hidden units, which is expected entirely. But the thing that's actually kind of surprising is that there seems to be a gap, and we weren't able to actually fully close this gap between the two models. And on top of that, the quantum model isn't gaining its power just because of the fact that it's got more parameters. This all-visible quantum model over here, given by the blue line, actually has fewer parameters than this dashed line at the top. Now, obviously, there's more work that needs to be done in order to give a full comparison between these two, but this gives a confidence that this intuition that the quantum models actually give richer models for data than classical models is somewhat borne out by this data. Another thing that I think is really kind of neat about this is that it also gives you a way to learn information about quantum states. So what we have is if we have a thermal state coming in here and we want to know what it is, we can effectively just learn this Hamiltonian H up here by using Boltzmann training and figuring out the weights. We do this, and it learns it great. After fewer than 100 steps, we're at machine epsilon for this, which is comparable to many alternative methods that have been come up for idiosyncratic reasons in the quantum literature. We can also use this in order to build an associative memory. So here I've trained a Boltzmann machine with 4 distinct patterns, loaded up with an address qubit that tells you which one you want to generate. Then I fix that address qubit and get the Boltzmann machine to generate. Lo and behold, it generates exactly those states on demand. So these Boltzmann machines can actually be really neat quantum memories. So in order to conclude, quantum computers can give really big speed-ups for classical machine learning problems, as we've seen, quadratic or better in most cases. But they also enable fundamentally different types of machine learning. And also, on top of that, they allow us to actually directly learn off of quantum states itself and allow us to understand at a deeper level what machine learning and artificial intelligence really means as we push beyond the classical world that we're at to the very edge of physics. Thank you very much.
All right, good afternoon, everybody. Is this? Yeah. So what I'd like to do today is basically assume quantum computers will not work for a long, long time or fail completely. And then see, well, what do we do? Now, I'm going to illustrate this by studying a currently working quantum device, and I refuse to call it a computer, which is a special purpose machine designed to actually optimize problems. And because I'm going to do a little bit of an arms race, I figured I'll keep tabs. On the left-hand side, you have the Planck constant equals 0, which means classical approaches. On the right-hand side, you have a finite Planck constant, which means quantum approaches. Now, there's a bunch of questions we would like to have answers to. One of them, of course, which I will address extensively, is what is the current status of quantum versus classical optimization? What about quantum approaches for machine learning? Here, I'm going very specifically not about what Nathan Wiebe discussed earlier, but going back to what you could do with current available quantum technology. And then, of course, what I just said before, if quantum annealing or quantum annealing as it is being done right now fails, can we still benefit? And coming back to the words that Matthias used, I'd like to just mention the think quantum inspired. Now, the results I will show you were done with a bunch of guys at Texas A&M that I work with, as well as some other folks. And I liked pop-up video way back when in grad school. And since Chris is here, and unfortunately he didn't make it to the photo, I figure I'll just pop him in there. Good. Why do we need quantum annealing? And the answer is simple, it's optimization. There's a lot of optimization problems out there. I'm willing to say that optimization is ubiquitous pretty much anywhere in all branches of science and also industry. And to give you an idea, we can pick just a handful of optimization problems, for example, constraint satisfaction problems. These are Boolean formulas. You want to basically find an assignment of the variables that at the end computes to true. You have the number partitioning problem. You have basically a set of objects. You want to split it up into a partition with equal weights. It turns out this is a very hard problem to solve. You have minimum vertex covers, which is where do you place your guards in a museum, usually between two rooms, because then you can watch two rooms. But what is the minimum number of guards? Turns out to be, again, a very hard problem. And one of the optimization problems that most people know, which is a traveling salesman problem, where you want to know what is the shortest route between cities. Now, these have a bunch of things in common. First of all, they have what I would call a very rough cost function or energy landscape. What I mean by that is that you can have solutions that are very similar. However, you would have to have a very large rearrangement of the variables to get from one solution to the other. In other words, if you, for example, have a traveling salesman tour, then a small perturbation to the position of one of the cities could cause a rearrangement of the tour that is order of the number of cities you have. Now, these are very nasty problems as seen from a physics point of view, because it means that your cost function landscape has deep valleys separated by very, very tall mountains. Another thing they have in common is that they are usually found in the NP class. Not only that, but if you were to look at the typical time it takes you to solve these problems, it is usually something very, very difficult. So even on average, you basically have to bite your teeth out to solve these problems. And finally, and most importantly, this, however, has to be taken with a grain of salt and is only presented here to motivate why people are building quantum annealing machines. With some overhead, you can map them onto what is known as quadratic binary unconstrained optimization problems. In other words, modulo massive, potentially massive overhead, you can always cast any of these problems or many more as such a quadratic form where you have Boolean variables and you basically have an interaction matrix Qij that kind of describes the problem you are trying to solve. And of course, the goal here is to find the minimum with respect to these Boolean variables. In other words, it's important to have good solvers for these things as well as fast architectures. I don't think I need to convince you guys in the audience that Moore's law is slowly coming to an end. Here is a picture of Moore's law. You can very nicely see that the transistor count doubles roughly every other year. And so if you want to overcome this end of Moore's law, we basically have 4 options at hand. We can say, fine, we'll just wait it out. You know, wait a couple of years, and you'll have twice as many transistors in your system. But the problem is that if we want to build larger silicon-based computers, we're going to encounter issues with power. If you wanted to build something that is exaflop, you will likely need of the order of gigawatt power. The other idea is, well, can we develop faster silicon technologies? And the answer is not quite, because we're reaching fabrication limits. And if I now add the clock speed to this plot of Moore's law, you see very nicely that roughly since the year 2000, the clock speed has more or less remained constant. So if you want to have any kind of disruptive technology, we have to actually go beyond standard silicon. In other words, come up with more clever chip designs, custom silicon type chips, or quantum architectures, but more importantly also invest in novel algorithmic advances. And here again, I'd like to just emphasize that the things that we do at Texas A&M are basically a mixture of physics, quantum information, as well as some computer science. Good. Now, what is the current state of the art in quantum optimization? The current state of the art, it's funny, Matthias showed the same device. It's not Antikythera, but it is a machine that basically is Antikythera reinvented 2,000 years later. These are special purpose analog quantum annealers. And these are machines that use quantum effects to actually try to minimize problems on these quadratic forms. Now, as Matthias mentioned, you can purchase yourself such a machine. It sets you back roughly about $10 to the $7. It's made by D-Wave Systems, Inc. And what is it? It's a semi-programmable machine. It's analog. It is made out of, in this current incarnation, roughly 2,000 superconducting flux qubits. What this means is that if your problem has 2,000 variables, in principle, you should be able to find the optimum to your problem on this type of machine. Controversial performance, as you will see in the next few slides. And more importantly, I like to emphasize that it's still a huge technological feat. Building such a device is highly non-trivial, and I'm sure that the Microsoft team that is playing with Majorana fermions is looking at something that is an order of magnitude even more complex than this. Now, what can this machine do? As I said before, it can minimize these quadratic forms post-embedding, and I will explain what I mean with this, onto the machine's fixed chimera topology. What is this thing? Well, basically, those quantum bits are hardwired together, just because it's not easy to do plug and play in these type of devices, and they are wired together in the topology you see behind me in the top left. You have these fully connected bipartite K44 cells that are then connected with their neighboring cells. So if you squint and you treat one of these blocks of 8 qubits as a unit, you have a two-dimensional lattice of variables. As you can imagine, this low connectivity combined with the analog noise is something that causes a lot of problems. The other issue with the low connectivity is that if you were to try to embed a problem that requires a fully connected graph, you would have a massive overhead. Now, how do these quantum annealers optimize? And the answer is sequentially. It turns out this is good old German technology. And for this, let me go back to the thermal analogon, which is simulated annealing. About 7,000 years ago, the Germans figured out in the Neolithic era that if you take a chunk of metal, you heat it up, and you cool it down slowly, you can remove imperfections, in other words, coming closer to the optimum, and therefore work your metal better, build a better axe, and whack somebody even harder. Okay? Now, we can do the same thing today on the computer. It's called simulated annealing. Basically, you start with your cost function. You add a temperature to it. It's a very high temperature, so the variables are continuously changing. And then you stochastically sample the cost function, and sequentially, you keep reducing the temperature slowly once it is thermalized. And when you go with temperature goes to 0, you hope to actually find the optimum to the problem. The slower you cool, the better, according to a theorem by Geman and Geman. If you cool infinitely slow, you will find the optimum, but this is by no means practical. Now, what is the issue that we face? If you use this technology on problems with rough cost functions, like the ones that I showed you before, it's very easy to get stuck in a metastable state. The way this is typically overcome is, instead of doing a slow anneal, you do very many fast, quick anneals. In other words, you rain down on the landscape, and like that, you hope to basically hit the jackpot. How do quantum annealers work? They basically do the same, except that the thermal fluctuations that you add to your cost function are replaced by quantum fluctuations. It's a sequential method like simulated annealing. However, you have an advantage. And the advantage is that since you have a quantum problem now, you don't have, or let me rephrase it, you have basically a quantum wave function that you slowly reduce its quantum fluctuations, meaning that if you encounter a barrier that is tall enough in your anneal, you might be able to tunnel across this barrier and therefore find the optimum, where a thermal type approach might get stuck. The way this is implemented on quantum annealers is using a transverse field. This is for the experts in the audience. You start with your original problem. You see you have added variable z here. You add a transverse field in the orthogonal direction. This induces quantum fluctuations, and then you reduce the amplitude of these fluctuations according to some protocol. Good. Now, I've told you why people want to build these quantum annealers, roughly how they work, and where you can get one, which you shouldn't. Now the question is, can they do anything useful? And if we rewind about 1.5 years back, there was a press release by NASA and Google claiming that this quantum device, or quantum-inspired device, might be 100 million times faster than classical technologies. Let me show you the results. You're going to see a couple of these plots. What you see here on the horizontal axis is the number of variables in the problem to be optimized. And on the vertical axis, you have the time to solution in microseconds. In other words, on average, how long did it take you to find the solution to a problem? For easier viewing, I'm just going to chalk in the 50th percentiles so that you can more or less see what's going on. And what you can see right away is that the thermal simulation has a much steeper slope. In other words, it scales far worse than the quantum approaches. Down here, the D-wave machine, and up here, you have quantum Monte Carlo, or simulated quantum annealing, which basically is take your quantum algorithm and run it on current classical hardware. So you can see the scaling of this is considerably better. However, we have a massive offset. Now, what are the problems that they studied? And this is just as a side comment. They took the native lattice that these systems have, this chimera lattice, and they took 2 of these K44 cells and wired them together ferromagnetically. What this means is, in the optimum, all the variables want to have the same value. But in addition to this, they added to their cost function a bias term. And one block had a stronger bias than the other one, meaning that when you thermally anneal, it's easy to get fooled into the wrong state and land in a metastable state. If quantum mechanics works and this thing is actually quantum, you might be able to tunnel through this barrier and then find the true optimum. Now, to make this hard, you take these, what they call weak strong clusters, and you string them together either with these red or blue lines that you see up here. What this means is, if you have a blue line, 2 of these clusters want to have their same values in the optimum. If they have red lines, they want to have opposite values. And as you can see, this becomes suddenly a very nasty constraint satisfaction problem. We call this the spin glass backbone. So let me go back to the results. If you now compare 10 to the 12 for thermal versus 10 to the 4 for the quantum machine, you get your 100 million. Having said that, you see that the scaling of this thing down here, and actually one should look only at the larger system sizes, the asymptotic behavior, is much flatter than for the thermal anneal. What if we now take the quantum algorithm run on classical hardware, the green line, and run it on better hardware? Think of, for example, Catapult and simulated quantum annealing or quantum Monte Carlo. We might be able to move this offset down and find a much better optimization technique. So I would say better scaling for D-wave and quantum-inspired algorithms. So coming back to my scoreboard, I would give it a 1-0. Needless to say, this was displeasing for me because I felt that there's many other algorithms out there. So we pulled out the whole battery of methods that we have at hand. And we looked first at algorithm tailors to the problem, which you see on top. Here we are actually exploiting the structure of the problem. We know what the problem is made out of, and we abuse it. And a simple example is what we did, this so-called superspin approximation, where we said we know that these weak strong clusters, the logical variables are unit blocks. So what we can do is we can just take the lattice and replace it by individual large logical blocks. Then you reduce the number of variables, and bam, you solve the problem. But we also used algorithms that are not tailored to the problems. They're generic methods that you can use for all kinds of optimization techniques, optimization problems. And we ran those. We used first population annealing Monte Carlo, also known as particle swarm method. And we also used a solver that we developed at Texas A&M, which is a mixture of what is known as parallel tempering and isonordetic cluster moves. We thought, well, this thing seems to work well. Let's send it to the MaxSat competition last year. And in our first submission, we actually won. Again, imagine what you could do if you toss this thing on Catapult. Just saying. Good. And then we compared to what was done by the paper by Google and NASA, which is simulated annealing quantum Monte Carlo and the D-wave. And now you see the picture changes. What you see here is fit now a line to these individual scaling plots and show the main leading scaling exponent. In other words, what is the slope? Which means that smaller slope is better scaling. And you see very nicely, if I color this in and I toss a line across the break-even simulated quantum Monte Carlo here, simulated quantum annealing here, that within the sequential realm of algorithms, like simulated annealing and so on, quantum does best, but even when we use our own solver that is not tailored to the problem, we massively outperform all these other techniques. Of course, this here I would almost call cheating because we're abusing the structure of the problem. So I would say that any speed up is sequential at best. And what I mean is that, we evened out the score. Fast forward a year, and D-Wave announced their machine with 2,000 qubits, accompanied by a paper that was basically saying, look, our new machine is so much faster than all the others. Let me show you the results. Again, you see D-Wave, the machine, and Quantum Monte Carlo have the same slope, but the slope is better than what you get with thermal simulated annealing. So again, what if we were to combine this, say, with better hardware? Now, these results have a problem, and the problem is the following. These so-called frustrated cluster loops, again, are a logical problem defined on a planar lattice. And what this means is you're optimizing a planar spin glass problem. In other words, this is bad news because you can solve this actually in polynomial time. So if I take the same results now and I use minimum weight perfect matching on them and compare now to the solver we used, take the D-Wave data, which I colored here in yellow, and this is our solver. Note that the axis changed from linear log to log-log, and you can see that we are exponentially faster than actually the D-Wave. So you gotta be careful when you make these claims, and especially if you read all these press releases, I would take them with a giant grain of salt. Good. I would say 2-1 for classical. Now, in the last couple of minutes that I have, I'd like to talk about something that is a key ingredient for machine learning, and this is fair sampling, something that is very important to me. What is fair sampling? It's the ability of an algorithm to find uncorrelated solutions to a degenerate problem, ideally with the same probability. Why is this important? Well, sometimes the solutions are more important than the optimum. Think of hash stats, think of probabilistic membership filters based on SAT or machine learning applications. And sometimes some solutions might be more convenient due to external constraints that were not considered to simplify the problem. So when you benchmark an algorithm, a good benchmark is, can I find the optimum fast and reliably? A much harder one is, can I find all minimizing configurations? And back in 2009, and I should say again, our solver turns out to be one of the fairest samplers out there that we could find today. So back in 2009, we decided to study a 5-variable toy problem. Again here, solid means variables want to be the same, dashed means they want to be in opposite values, and you can actually go and integrate the Schrödinger equation. You can do the whole simulated quantum annealing study, and what you will find is that state 1 is exponentially suppressed. This is probability of finding the state as a function of time, and states 2 and 3 appear 50% of the time. And this is kind of a bad sign if there is a state that you can never find in your quantum evolution. Well, what about quantum annealing machines? We went in, we designed problems very carefully that have a very well-curated number of ground states, and we then ran this algorithm many times, or this problem many times on the quantum annealer. And what you will see in the next slide is, if there is fair sampling, you would expect to find a histogram that is roughly flat, modulo Poisson fluctuations. If the sampling is unfair, you would expect something like that. Briefly show you the data. As you can see, this is a logarithmic scale. This was run on the quantum annealer by D-Wave. And you can see that if you do quantum annealing with a transverse field, you're massively biased. In other words, you will need to tweak transverse field quantum annealing if you want to use a quantum annealer for sampling. Good. With this, I'd like to slowly come to an end. I think it doesn't look too good, but I want to emphasize that this is for analog quantum annealing on current hardware. Okay, this makes a lot of assumptions as to what the quality of the hardware is. And IARPA has recently started a program based on quantum enhanced optimization. You can wait 5 years, find out if better qubits will give you better results, or maybe by then we will be superseded by digital devices such as the ones being worked on by Microsoft. And with this, I'd like to finish. Hopefully I'll be able to show you that classical optimization pushes quantum developments, but at the same time, quantum developments leverage classical new algorithms that are very fast and much better than the things that we've been using for a long time in physics. Machine learning could benefit from quantum annealing if we can teach it to sample fairly. And finally, to date, there is no real application speedup that has been found. So far, we can still squash any quantum annealer with classical hardware. Thank you.
Great, thank you. Thank you, Helmut. And Matthias and Nathan, can you come up? Grab a chair. Great. So now we have time. We have about 20 minutes for questions. We've heard, I'll start with a question and then we'll open it up to the audience. We have runners on the sides here with mics. So if you have a question, feel free to raise your hand early and they can get a mic to you. Thank you all for wonderful talks. We covered a large space. We've covered everything from using machine learning to learn about quantum physics itself. And then in the end, looking all the way to actually maybe having classical approaches that outperform quantum approaches in cases. And then hearing more about digital solutions from Nathan during the second talk. Where else do you think we can learn from these quantum methods, from quantum mechanics and quantum algorithms, to see improvements in classical machine learning and AI applications?
Well, I mean, one of the things that at least we've run into in the past with some of our work is that sometimes there actually are solutions that you need, creative solutions that you need to come up with, at least on the quantum algorithm side, in order to be able to kind of fit the problems that we naturally but we want to solve in machine learning to a quantum computing setting. And that forces you to sometimes try some unorthodox approaches to sampling and other algorithms. And sometimes just forcing yourself to look down a very unorthodox path of things can lead you to very different solutions that have very different use cases than the standard methods that are being employed. So that's one way in which I found that it's been helpful to us.
Yeah, I think we saw nicely in Helmut's talk how competition from quantum devices that people build already makes people think about new approaches, makes people look back at how did we do physics-inspired methods in the past, and now there's the new generation of methods. So this 3.1 is actually extremely good news for the field, that by the quantum competition, the early one, we have made huge progress in classical technology that's useful immediately while we wait for the quantum machine to be ready. And just this quantum viewpoint can give you new ideas, like Nathan said, yeah.
Terrific. And so in terms of, in the last talk we spoke mostly about analog devices. What do you see as the power of the digital quantum computer? What could it gain over, for example, these methods we saw in Helmut's talk at the end?
Well, I mean, I think that the obvious big advantage of digital devices is that you can error correct them. So there's the questions that you were raising about the noise, for example, in the couplers and the D-wave system and how those can impact the quality of solutions. With digital approaches, at least in principle, even if you wanted to do exactly the same thing, you could at least use error correction to make those qualities arbitrarily good. On top of that, the other thing that having a digital device allows you to do, or at least a gate-based device that's universal, is it allows you to really, I think, bring to bear, for one, improve quantum sampling techniques that can give you a quadratic improvement on the number of samples you need to take from the system, like amplitude estimation, for example. The other thing is you can apply quantum simulation, which allows you to simulate and apply physics models that can't be employed on classical or near classical, like a stochastic Hamiltonian like you see in D-wave. So I think those, to me, stand out.
Yeah, I agree that basically analog machines have a limited set of applications. They were built, in this particular case, just to optimize. And you can always cast any other problem as an optimization problem, but that is not going to scale in the long run. And I guess the best way to summarize why we should look at digital versus analog is, why should I buy a Betamax if I can buy a Blu-ray DVD? That's basically what it boils down to.
Great. Are there questions in the audience? Let's open it up. I see a couple.
Mark Hill, I'm at the University of Wisconsin and also with the Computer Community Consortium. So this latter organization is about catalyzing research by getting researchers, research funders, and research customers together. With all that's happening in industry, what do you see that there's more opportunity to catalyze research in quantum computing, or is all going as fast as it can?
There's lots of opportunity, because what we do at the company here is now we want to take something that people have shown exists and can be done, and we want to scale it up. That needs massive investments in the engineering. But we always need new ideas. We need new ideas for new hardware. We need new ideas for new algorithms, new applications. So we always need people to come up and bring new ideas. And once we have a quantum computer, we need people to use it, to learn how to program it. So, so this just makes the field much, much bigger than before.
So another question in front.
Hi, I'm Pedro Dominguez from the University of Washington. If it's hard to design quantum mechanical versions of neural networks because quantum mechanics is linear and neural networks are non-linear, why not use quantum field theory instead?
Okay, so that's a very good question. One of the big problems with quantum field theory is that, at least, if you take a look at we've got a few that we know we can simulate on quantum computers, but in general, we actually don't know that we can efficiently simulate all field theories. For example, we don't have a rigorous proof that we can simulate the standard model efficiently on a quantum computer. We strongly believe, for aesthetic reasons, that it's likely true. But it's very difficult for us to begin with a Lagrangian formulation like you normally do with a field theory, and then translate that over to a series of quantum gates that we can execute. And I think that solving that problem is an important open question in quantum computing and in quantum simulation. But in general, we don't know really how to effectively deal with this. And one of the issues is that we actually even have, in some cases, some no-go theorems, because if you've got two quantum state vectors that are nearly parallel to each other, and those are the inputs to your algorithm, we have bounds that say you need a minimum number of copies of this state that depend on the inner product between the two. With a strong nonlinearity, we can separate those two. And so if we could actually implement that physically, we'd violate these lower bounds, and we'd have a contradiction. So what needs to be done to some extent, if we want to kind of implement these nonlinearities from the ground up, is really we kind of sort of need to do them, I feel, on the classical end before we feed them into our quantum computer. So we should use classical computers for what they're good at, i.e. nonlinearities. And we should use the quantum device for what it's good at, linear algebra and sampling.
Great. Are there other questions in the audience? Oh, yes, there's one in the back in the middle.
Yeah.
Oh, okay, well, we'll start here and then we'll go to the back. Kristen.
Hi, thanks for the talks. I'm Kristen Lauder, Microsoft Research Cryptography. I wondered about your comment about using quantum computers in a positive way to help protect privacy. We're all used to quantum attacks on polynomial quantum attacks on traditional crypto systems. So I wondered what you meant by that.
Sure. Yeah, I didn't unfortunately have time to go into this. So there's a number of different ways we can do this. One way, a lot of these stem from the original idea of quantum key distribution, which allows us to, to be able to communicate in a perfectly secure way without making any cryptographic assumptions between two parties, starting with a small amount of random key to begin with. But the key point is that what you can do is you can do things like blind quantum computing, which allow us to do something very similar to homomorphic encryption. But it's not protected by complexity assumptions about the cryptography. It really is honestly protected by the laws of quantum physics. So we can use this in order to securely, in order to secure our training data and apply an ML algorithm. But recent work that we've done has actually shown you can do tasks using very similar reasoning, like k-means clustering, in a private fashion, where you can bound the maximum amount of information about the ownership of any training vector that's submitted to the algorithm. So, for example, you could learn an adversary can learn means in principle out of this, but they could never learn whose medical data they contributed to a quantum classifier. And so these are the sorts of things that we can play, and we can use the fact that anytime you measure a quantum system in general, you disturb it in order to limit the impact that an adversary can have without being detected.
Great. Question in the back.
Yes, hello, David Poulain, Université de Sherbrooke. So you've compared the performance of the D-Wave machine with optimized classical algorithms, but the D-Wave machine is an analog device. So has anyone compared it with an analog classical computer?
We're in the process of doing that right now, actually. We got our hands onto, it's a digital machine, but it can be run in a semi-analog mode with limited precision. And we're doing that as I'm speaking right now here.
So I have one addition here, namely you can run that machine slightly warmer. That is basically a classical annealer. So you can run that machine in a classical mode. When you do that, my prediction is that for most problems it may even be better than when you run it in the quantum mode. So you have to pick the best algorithm for the application, whether you use the quantum or classical. And that machine, if you buy one, you can change the temperature and you can run it in both.
Actually, if I may add to that, so if you allow more random fluctuations in temperature, you get better sampling of states too. So if you use the machine not in the way it's intended, it turns out to be a better sampler than when you think you're doing it with quantum mechanics.
Thank you.
Great. Are there other questions in the audience? If not, I'll ask another question. So we've spoken about analog versus digital devices. When we look at the early digital quantum computers, what do you think those key first applications will be?
I think that the key first applications are likely going to be the things that most closely match the hardware that we have. And from that perspective, at least with the sorts of technologies we're looking at Microsoft, I honestly think simulation is likely going to be the first application, because it just so naturally matches the physics of the devices that we're going to have. I think that then once we go beyond simulation, as Matthias pointed out in his slides, once we push towards the couple thousand qubit range, then we can do things like the quantum Boltzmann machines that I talked about on a bigger scale. But one thing that I think is actually kind of evocative that we could do on a much smaller scale is we could use technologies like this to try to understand our quantum hardware in a slightly faster way than what we could do with our classical hardware. Not looking for a big speed up with this device, but just some understanding of what's going on in the quantum system. And that could give us information we need in order to design better quantum computers, which give us better quantum AIs, which give us better quantum computers. And the hope would be to use this to, in a virtuous cycle, to bootstrap on top of each other, to give us really the devices we want to be able to do things like quantum MNIST.
I think that just having a machine with 100 good qubits will let us play with it, explore it, learn new things, invent new algorithms, then train more students, and it will have a big impact. So the application will be learning, understanding, and training. And who knows, these machines with about 100 or 200 qubits are bigger than anything we can simulate on Earth. So there may be lots of potential in there for AI that we have to find and dig up.
Yeah, I agree. I think that the first developments of small-scale digital quantum devices will be basically toy computers to develop new algorithms on them, which is, I think, where most of the development right now is needed.
So as we think about these, the development of toy algorithms on these small devices, It reminds me that we're sitting at the faculty summit where we have many people from academic departments in the audience thinking about educating the next generation of quantum physicists and quantum computer scientists and machine learning theorists and practitioners. How do we go about training and teaching to this new way of programming and designing algorithms that are hybrid in nature between classical and quantum?
Well, when I talk to my colleagues, then they tell me that actually Microsoft is doing the community a big disfavor by grabbing me here. So what we have to do is we have to let me keep teaching people. We have to bring in people here. We have to make tools available to others. We have to share our knowledge with others, and we have to invite others to join us.
So I agree with Matthias that as a company that has the means to actually make really big developments in a fast pace, it would be great to see more open sourced tools and also access to potential devices to have academics play with and teach with. But as somebody who is in a physics department, I always have to explain people that what I do is physics, because continuously I'm told, well, you're not a physicist. And I think that one of the biggest barriers right now in teaching this in an academic environment is the fact that there's a balkanization between computer science, engineering, physics, mathematics. And so interdisciplinary centers need to be created, and companies like Microsoft could leverage such centers at institutions to basically foster the teaching of these new disciplines.
One thing that I think really we really need is that we really need to also create the art of quantum computer programming. I mean, so far what we have is our main resource in this is a textbook that at present is over a decade old and doesn't have many of the new innovations or many of the new tricks. At present, if somebody wants to learn how to, say, employ a state-of-the-art quantum simulation algorithm, then there's an entire chain of papers that they have to go through and learn in an idiosyncratic fashion. And we haven't figured out the right way to consolidate and communicate these tools and concepts so that people can rapidly learn. And I think we really need to do that in order to actually really start leveraging all the knowledge that the specialists have.
Yeah. You raised a good point, Helmut, namely, I also did not fit in well at ETH. People in physics didn't think I'm a physicist. They were not sure whether I'm an experimentalist or an engineer or whether I'm in computer science. And what's great here at Microsoft is that nobody even asks you what you are. So it can be all of that. I think that's something that we should bring back, that we break down the barriers between fields. Because what you need in quantum computing, you need physics knowledge, mathematics, computational science, computer science, algorithms. You need it all. It's engineering and science. And we have to break down barriers and make the world open.
So I often get the question from undergraduate students, what should I do if I want to work in this field? What is your recommendation to them?
Get a PhD.
In what?
Get a PhD. Really, I mean, I think that one of the things is that getting a PhD in physics, computer science, or mathematics, those can be great. In some cases, even getting a degree in chemistry can be fine. The key thing is, I think, in all of those areas, it's really increasingly important to learn the tools that have been developed in other fields. I think that we can't get by just by limiting ourselves to one particular area if we want to really honestly be good at quantum sciences. So, you need to get a PhD more importantly than you need to get a PhD, I feel, in a particular field.
If I may add to that, that assumes that you have faculty members that understand the interdisciplinary nature needed to get a PhD that will serve you later for working in that field. So I have one student here. He's slouching in his chair over there, and I think from what I've heard discussions with him, likely being able to be an intern for example, at Microsoft, where you can learn from all these fields at once, is probably key in starting to build up for a degree in that direction.
Are there any final questions from the audience? Okay, if not, I'll ask one more question. So what are you most excited about seeing in this field, kind of at the intersection of quantum computing and AI and ML in the next few years?
When I started doing science, I didn't know what to study, but I just knew I wanted to do science with great new computers. And just having something totally amazingly different and new for doing anything in science is exciting. And then we'll find out what we solve first and what's second and what third.
I mean, the things that I'm most interested in are two things. The first is, I think that when it comes to quantum computing, we really have, for a long time, dramatically underutilized machine learning in actually figuring out ways to calibrate and characterize our quantum systems. These tools have started coming into use, but we really haven't fully leveraged them. And I'm very excited within the next few years to see what some of these new developments, in particular ideas like reinforcement learning, might end up giving us in error correction or in other areas. But conversely, I'm also curious to see what quantum machine learning ideas can give us in terms of characterizing physical systems themselves. It seems that there's a great potential to use one tuned quantum system in order to interrogate another quantum system and do experiments that we wouldn't be able to otherwise carry out. And so I'm very excited to start seeing real experiments of that form being performed.
Helmut?
So I've always been very interested in solving hard problems. And in the past, you could say, well, who cares about what we were doing? But it was hard. That was what really interested me. And I've come to realize in the last few years, mostly because of this field, that there's a lot of problems out there in the real world that are hard and that need to be solved. And I think that both AI and quantum are tools that will allow us to solve these hard problems much easier in the near future.
On that note, please help me in thanking our speakers again for a wonderful session.
Thank you.
Thank you all. And thank you all for attending today.